Welcome to our sixth lecture. This week we're going to finish talking about chapter 13. Last week we introduced the idea of partial derivatives. We're going to extend this idea to the idea of directional derivatives and gradient vectors, and then we'll do some applications. We'll talk about tangent planes and differentials, extreme values and saddle points, and then finally we'll talk about Lagrange multipliers. I'm going to start by a quick recap of partial derivatives. What do partial derivatives mean in terms of pictures? For partial derivative, we're interested in how does the function change if we fix one of the variables and we let the other one change. So for example, if we say that y is always equal to y0, in other words, if we're in this green plane, we can ask, how does the function change when we vary x? Or we might want to fix x. We might want to say x is always equal to x0. We might say we're always in this orange plane, and then we could ask, how does the function change when we let y change? But we can extend this. We don't have to use these two planes. We could use any plane. Again, I'm looking at the point x0, y0, z0, and I'm looking for a vertical plane passing through these points. But of course, there are infinitely many vertical planes that we could choose, because we could choose any angle that we wanted. And then once we're in this plane, we could ask, how does the function change? What is the slope of the function if we insist that we're going to stay inside this green plane? This is the idea of directional derivatives, like partial derivatives, but now we can use any direction that we want. Let's have a look at a top view. Let's suppose we're looking down from the top. And we can see the x-axis and we can see the y-axis, and we have a point P0 in the xy plane. Now, if we're looking down from the top, a plane just looks like a line. And then we can ask, what is the derivative of f at the point P0 in the direction of a unit vector which is pointing in the same direction as this green line? And the answer is, now we're letting x and y change, but they're not changing equally. They're changing related to the orange vector. And we're going to insist that the orange vector is a unit vector. So now instead of x0 plus h and then leaving y0 as it is, or x0 left as is and y0 plus h, we're changing both the x coordinate and the y coordinate, and we're changing them as multiples of u1 and multiples of u2. We write this type of derivative as capital D, subscript u, subscript the unit vector, f, and then open brackets at the point P0. And that's equal to this limit if this limit exists. There's another way to write a directional derivative. We could write it as open bracket df ds, close bracket u comma P0. I prefer the notation on the left. I think it's easier to understand which is the point and which is the vector if we use the notation on the left. And easier to understand that this is a directional derivative. It's not the ordinary derivative that we're used to from before. Let's look at an example from the book. Here's the definition in the blue box. The directional derivative at the point p0 in the direction u is given by the limit as s tends to 0 of f at x0 plus su1, y0 plus su2 minus f at x0, y0 divided by s. What does the question say? The question says, find the derivative of x squared plus xy plus xy at the point 1, 2 in the direction of the unit vector 1 over root 2i plus 1 over root 2j. So to answer this question, we're going to plug this function, this point, and this unit vector into the formula, into the definition, and we're going to see what we get. The point is the point 1, 2. So that gives us our first numbers, 1, 2, 1, 2. The unit vector is 1 over root 2, 1 over root 2. So there's a 1 over root 2 here and a 1 over root 2 here. And then when we calculate the function, x squared plus xy, and simplify, and I'll leave this all for you to check, we get the answer to this question, which is 5 over root 2. To say this another way, as it says at the bottom, the rate of change of x squared plus xy at the point 1, 2 in the direction u is 5 over root 2. So yes, we can use this definition, this limit, to calculate directional derivatives, but it's easier if we calculate gradient vectors. Now at this point I'm going to take a 5-minute break because I'm struggling to get my files uploaded into the system this time. I'm getting lots of error messages, so quick 5-minute break while I sort out the technical difficulties. Okay, let's continue. I've got the next batch of slides uploaded. Okay, so we talked about directional derivatives, and I showed you the definition and how it's possible to use the definition, but in practice, that's not how we calculate directional derivatives. In practice, we calculate directional derivatives by using gradient vectors. But what is a gradient vector? Again, let's suppose we have the graph of a function of two variables, z is equal to f of x and y, and a point on this graph. And let's suppose that you are standing, this is my drawing of you, let's suppose you're standing on the point x, y, z, x0, y0, z0. And then I could ask you which way is uphill and which way is downhill from your perspective. Let me rotate this around a little bit. Okay, so imagine you're standing on a hill or on this graph, and I asked you, what is the direction that goes uphill? Then you would answer this way. This is the way that you would walk if you were asked to walk uphill. Or let me ask this another way. Let's suppose you put a ball on the surface at the point x0, y0, z, and then you let go of the ball. Which way will the ball roll? It's going to roll downhill, right? So it's going to roll this way. Again, let me rotate this graph a little bit. If we put a ball on the point x0, y0, z0, we'd expect it to roll down the hill like this. It's going to roll in the opposite direction from the arrow I've drawn in orange. So remove the graph, and let's project this orange arrow down onto the xy plane. This green arrow is called the gradient vector. It points in the uphill direction. Which direction do you walk in the xy plane if you want to walk uphill? Or what is the opposite of the way that the ball will roll if you put a ball on the surface? The length of the arrow tells us how steep the slope of the hill is. If we have a steep slope, we're going to have a long arrow, a big gradient vector. If we have a shallow slope, then we're going to have a short arrow, a small gradient vector. Okay, great. That's what gradient vector means, but how do we calculate it? Here's the definition. The gradient vector of the function f is the vector nabla f, which is df dx I plus df dy j. This is a vector, so it's a number. At each point, it's a number multiplied by I plus a number multiplied by j. It's also a function because f of x and f df dy are functions. This symbol, this upside down triangle, is written as either nabla or it's written as, it's pronounced either as nabla or it's del. Why nabla? Because nabla is an old Greek word for a harp. I've written the formula at the top. Nabla f is df dx I plus df dy j. And for our first example, find the gradient vector of x e to the power y plus cos xy at the point 2, 0. So what do we need to do? We need to calculate the partial derivative of f with respect to x at the point 2, 0. We need to calculate the partial derivative of f with respect to y at the point 2, 0. And then we're going to put these into our formula. Fx at 2, 0i plus Fy at 2, 0j. So remember how we do partial derivatives. For the first one, we're doing the partial derivative with respect to x. So we're going to pretend that y is a constant. We're going to ignore the y terms, and we're just going to differentiate the x terms. The derivative of x e to the power y is then just e to the power y. Y stays the same. Derivative of x is 1. Derivative of cos is sine. By the chain rule, we also need to multiply. Sorry, it's minus sine, and by the chain rule, we also have to multiply by y. Calculate this at the point 2, 0. We get e to the power 0 minus 0 or 1. Next, we'll do the partial derivative of f with respect to y at the point 2, 0. Derivative of e to the power y is just e to the power y. So the first time is x e to the power y. Again, the derivative of cos is minus sine, and this time by the chain rule, we get an extra factor of x. Then replace x by 2 and replace y by 0, and we get 2. Now we're ready to write down the gradient vector. It's going to be 1i plus 2j. And that's it. It's just calculating two partial derivatives and then using the definition of the gradient vector. And this means the uphill direction, if we think of the graph of a function of two variables as a hill. Okay, great. I said that we could use gradient vectors to find directional derivatives. So how do we do that? Here's the theorem. The directional derivative of f in the direction u is always the same as nabla f dot u, the dot product of two vectors. And in practice, this is what we're going to be using. In practice, we're going to be calculating the gradient of a function. Nabla f is df dxi plus df dyj. And then we're going to do the dot product of the gradient vector with our unit vector u. So let's do an example. Find the derivative of x e to the power y plus cos xy at the point 2, 0 in the direction of 3i minus 4j. This is the same function that we've just done. We know the gradient vector of f at the point 2, 0. We've just found that it's I plus 2j. Next, we want to find the direction derivative of f in the direction of u. Sorry, in the direction of v, but v is not a unit vector. We need to find a unit vector u which points in the same direction as v. How do we do that? How can we always find a unit vector pointing in the same direction as v? We just divide v by its norm. So our unit vector is going to be 3 over 5i minus 4 over 5j. And then we're almost finished. All that's left to answer this question is to calculate the dot product of these two vectors. And I'll leave it for you to check that the dot product is equal to minus 1. So what that means is, if we were standing on the graph of this function at the point where x is 2 and y is 0, And if we were facing in the same direction as 3i minus 4j, then the ground underneath us would slope downwards at slope -1. Now, note that the directional derivative of f in the direction u, that's nabla f dot u. We have a formula for the dot product. That the dot product of a and b is norm of a, norm of b cos theta, where theta is the angle between the vectors a and b. So we'll use that here. We get norm of nabla f, norm of u, cos theta, where theta is the angle between nabla f and u. But u is a unit vector, so we can forget about the norm of u, and we just get norm of the gradient of f multiplied by cos theta. Cos theta is always between -1 and 1. So the directional derivative of f in the direction u is always going to be a number between minus the norm of nabla f and the norm of nabla f. The biggest possible value of a directional derivative is the norm of the gradient, and the least possible value of a directional derivative is minus the norm of the gradient. How can f increase most rapidly? How can we get the biggest possible directional derivative? We get the biggest possible directional derivative when cos theta is equal to 1. We get cos theta equal to 1 when the angle between them is 0. So we get the biggest possible directional derivative when u points in the same direction as nabla f. That's a proof of what I said earlier today. The directional derivative, so the gradient vector, we can think of as the vector which points uphill if we were standing on the graph of a function. And how could we get the least possible directional derivative? How could we get f to decrease most rapidly? The smallest of directional derivatives could be, the lowest number it could be, is when we have cos theta equal to -1. That's the same as saying that theta must be 180 degrees, or u points in the opposite direction of nabla f. So if we put a ball on a hill, if we put a ball on top of the graph of a function, the ball must roll in the direction minus nabla f. This is the proof of what I said earlier. And also note that if the angle is 90 degrees, if the angle between the gradient vector and our unit vector u is 90 degrees, then cos theta is 0, so the directional derivative must be equal to 0. Okay. An example from the textbook. Find the directions in which x squared over 2 plus y squared over 2, part A, increases most rapidly at the point 1, 1. That's going to be the same direction as the gradient vector. Decreases most rapidly at the point 1, 1. That's going to be the opposite direction from the gradient vector. That's going to be in the direction of minus the gradient vector. And part C, what are the directions of 0 change at f? That's going to be when the angle between our unit vector u and the gradient vector is 90 degrees. So let's answer these 3 questions. First, the book says the function increases most rapidly in the direction of nabla f at the point 1, 1. So to answer this question, we calculate the gradient at the point 1, 1, and then we find a unit vector pointing in that direction. Let's move on to part B. As the book says, the function decreases most rapidly in the direction minus nabla f. So that's the opposite from the previous example. Just take the answer to part A and put a minus sign in front of it. And the directions of zero change are the directions orthogonal to nabla f. The directions where the angle between u and nabla f is, or in this case n, and nabla f are 90 degrees. So that must be minus 1 over root 2i and plus 1 over root 2j and minus that vector. Let's briefly talk about some algebra rules for the gradient vector. Gradient vectors just uses the partial derivative. So pretty much everything we know for partial derivatives is also true for gradient vectors. There's nothing much to prove here. The rules that you would expect to be true are all true. The sum rule, nabla f plus g is nabla f plus nabla g. The difference rule, there's a typo here, should be minus. Nabla f minus g is the same as nabla f minus nabla g. Constant multiple rule, of course, nabla kf is the same as k nabla f for any number k. The product rule, nabla fg is the same as g nabla f plus f nabla g, just as we would expect it to be. And the quotient rule is the same as we would expect it to be. Nabla f over g is equal to g nabla f minus f nabla g over g squared. Back to the book for an example. In this example, we're going to illustrate two of these rules using the functions f is x minus y and g is equal to 3y. Of course, nabla f is I minus j, and nabla g must be 3j. Nabla f minus g, that's nabla x minus 4y, is I minus 4j, or that's the same as nabla f minus nabla g. And to show that the product rule is true for these functions, f multiplied by g is 3xy minus 3y squared, and the gradient of that vector is 3yi plus 3x minus 6yj. And of course, that's the same as f nabla g plus g nabla f. We've been talking about functions of two variables. What do we do if we have a function of three variables? We just add on an extra term. Now that we have a z variable, we're just going to add on df dz k. That's the only difference. Still, we have that the directional derivative of f in the direction u is nabla f dot u. So, for example, find the derivative of x cubed minus xy squared minus z at the point 1, 1, 0 in the direction of 2i minus 3j plus 6k. And then part B, in which directions does f change most rapidly at p0? That's going to be the same as the gradient vector. And what are the rates of change in these directions? So to answer part A, first we need the direction of V. In other words, first we need a unit vector which points in the same direction of V. So here we are, we're going to be using U is 2 over 7i minus 3 over 7j plus 6 over 7k. We also need the partial derivatives of f at the point p0. So here we go. Fx at the point 1, 1, 0, we can calculate is 2. Fy at the point 1, 1, 0, we can calculate is minus 2. And Fz at the point 1, 1, 0, we can calculate is minus 1. After we know these, we can write down the gradient vector of f at the point 1, 1, 0. The first partial derivative is 2, second one is minus 2, and the third one is minus 1. So in the gradient vector, the first number is 2, the second number is minus 2, and the third number is minus 1. Then we want to calculate the derivative of f, that's the directional derivative of f, at the point p0 in the direction v. So we use our formula. Directional derivative is gradient of f dot product with u. Now we know the gradient vector, now we know u. We just calculate their dot product. And I'll leave it for you to check that their dot product is equal to 4 over 7. Part B asked, in which directions does the function change most rapidly, either increase most rapidly or decrease most rapidly, and what are the rates of change in those directions? As we've talked about, the function increases most rapidly in the direction of the gradient vector of f, and it decreases most rapidly in the direction of minus nabla f. And the biggest possible value for the directional derivative is the norm of the gradient vector of f. If I was writing it, I would use 2 double lines. Double line, nabla f, double line, and that's equal to 3. And the least possible value of the directional derivative is minus the norm of nabla f. So the smallest possible number for the directional derivative is minus 3. Now I need to move to the next file. And again, I'm having trouble uploading this. So we'll take a break here and I'll continue at 2 o'clock. And now let's continue. We still have 3 sections to talk about this week. Our first of these 3 sections is tangent planes and differentials. I talked about the gradient vector as the uphill direction, but there's another way to think about it. If we think of a surface as an equation involving x, y, and z equal to a constant, then we can think of the gradient vector as the direction that we go if we increase this function. What that means is the gradient vector is always orthogonal or normal to this surface at this particular point. So if we were asked to find a tangent plane, it would be the plane with normal vector nabla f. If we were asked to find a normal line through a point on the surface, then we're asking for the line which passes through that point parallel to nabla f. So, formal definition, the tangent plane to the surface f of x, y, and z is equal to a constant c at the point P, and this is important where the gradient is not 0, is the plane passing through the point P with normal vector gradient of f at the point P. Now, because the gradient vector of f is partial derivative of f with respect to x, I, plus partial derivative of f with respect to y, plus partial derivative of f with respect to z, the numbers in our plane equation are going to be fx at p, fy at p, and fz at p. So this is the formula that we can use. The normal line to the surface, f of x, y, z is equal to c at the point P, is the line which passes through the point P parallel to the gradient vector of f at the point P. And we can write down parametric equations for this line. It's going to be x is x0 plus fx t, y is equal to y0 plus fyt, and z is equal to z0 plus fzt. Using these definitions, we can do an example. Find the tangent plane and the normal line of the surface x squared plus y squared plus z minus 9 is equal to 0 at the point 1, 2, 4. I don't have a picture of this. You can find the picture in your textbook. We want to use the definitions. First thing we need is we need to calculate the gradient vector. So here we go. You know how to do this now. The gradient vector of f at the point 1, 2, 4 is 2i plus 4j plus k. And then the next thing is to calculate the tangent plane. We use the numbers from the gradient vector, that's 2, 4, and 1, in the formula. So it's 2 something plus 4 something plus 1 something is equal to 0. What are the somethings? The somethings are x minus x0, y minus y0, and z minus z0. Rearrange this and we get the standard form. The standard form for the equation of a plane is going to be 2x plus 4y plus z is equal to some number. In this case, the number is 14. And using the definition for the normal line, we take our point first of all. The point is 1, 2, 4. That's 1, 2, and 4. And we use our gradient vector. The numbers in the gradient vector are 2, 4, and 1. 2, 4, and 1. We can write down quickly that x is 1 plus 2t, y is 2 plus 4t, and z is 4 plus t. And that's all we need to do. Now let's think about z is equal to f of x and y. That would be the same as writing f of x and y minus z is equal to 0. Or if we have this new function, capital F, it's the same as writing capital F of x, y, z is equal to 0. So using that idea, the tangent plane to the surface z is equal to f of x and y. That's the same as saying the tangent plane to capital F is equal to 0. So just adapt the ideas from the previous few slides. The tangent plane then must be fx, x minus x0, plus fy, y minus y0. D capital F dz is just minus 1, so minus just here. Z minus z0 is equal to 0. Using this new definition, this new formula, we can do another example. Find a plane tangent to the surface z is equal to x cos y minus y e to the power x at the point 0, 0, 0. So what do we need? We need the partial derivatives of small f with respect to x and y at the point 0, 0. I'll leave it for you to check that these are 1 and minus 1. And then we use the formula from the previous slide to write down that the tangent plane must be 1, x minus 0, minus 1 from the second partial derivative, y minus 0, minus z minus 0 is equal to 0, and rearrange that, we get x minus y minus z is equal to 0. There's two types of tangent plane questions here because you can be given the formula in two different ways. You're either going to be given a function of x, y, and z is equal to a number, then you use the first formula, or you might be given z is equal to a function of x and y, and then you use this second formula. Or you rearrange your equation so that it looks like the first form. The surfaces x squared plus y squared minus 2 equal to 0, that's a cylinder, and x plus z minus 4 equal to 0, that's a plane, meet in an ellipse. Find parametric equations for the line tangent to this ellipse at the point 1, 1, 3. Let me show you a picture. We have this cylinder, x squared plus y squared minus 2 is equal to 0, and we have this plane, x plus z minus 4 is equal to 0. And the intersection of this cylinder and this plane is an ellipse, which is written in light, it's drawn in light blue in this picture. We are asked to find parametric equations for the tangent line to the ellipse at the point 1, 1, 3. So if I can try to draw on here. We're asked to find parametric equations for this red line. Now, you can see here that our line is going to be parallel to the vector nabla f cross nabla g. Why? Because the tangent line is orthogonal to nabla f at p0 and it's orthogonal to nabla g at p0. If we want to be orthogonal to two vectors, what do? We take their cross product. So this line is going to be parallel to nabla f cross nabla g. So we're going to calculate nabla f, we're going to calculate nabla g, and then we're going to take their cross product. Here's the calculation. You can check this at a later date. Let's not spend time talking about it now. You can check that nabla f cross nabla g at the point 1, 1, 3 is 2i minus 2j minus 2k. And as soon as we know that, we know a point on the line and we know a vector which is parallel to the line. So straight away, we can write down the answer. X is 1 plus 2t, y is 1 minus 2t, and z is 3 minus 2t. I've been deliberately quick here. You can read this example in your textbook. The next idea, I want to slow down a little bit, is linearization of a function. You did this in mathematics 1. You did linearization of a function of one variable in mathematics 1. And the idea is this. We have some function, y is equal to f of x, and we have some point on the graph of this function, the point a, f of a, and I want to calculate the linearization of this function at the point a. And what this means is the tangent line is the line which passes through the point a, f of a, which has the same slope as the graph at this function. And this should look familiar to you if you remember back from what you did in mathematics 1. This linearization is defined to be L of x is f of a plus f prime at a multiplied by x minus a. That should all look familiar to you. But now I want to move to two variables. Typo here, two variables. The linearization of a function f of x and y at the point x0, y0, same type of thing. We start with f at x0 and y0. We have a derivative at this point multiplied by x minus x0, and then because we have two variables, we have another term. A derivative at the point multiplied by y minus y0. Exactly the same ideas that you learned in mathematics 1, but just with an extra term. An example from the book. Let's go faster again. Find the linearization of x squared minus xy plus a half y squared plus 3 at the point 3, 2. What do we need? We need f at 3, 2, fx at 3, 2, and fy at 3, 2. I'll leave it for you to check that these are 8, 4, and minus 1. And then after we know these, we use the definition. Underlined in red, we're asked to calculate L of x and y, that's f at x0, y0 plus fx at x0, y0, x minus x0 plus fy at x0, y0, y minus y0. Stick the numbers in and we get our answer. I will leave it for you to check that the answer to this question is 4x minus y minus 2. Now I need to move to my next file. Section 13.7 is about extreme values and saddle points. Think of the graph of this function of two variables. I've drawn a function which goes up and goes down, and I've labeled 3 points, 2 local maxima and 1 local minimum. You talked about local maxima and local minima, local extrema in mathematics 1. We're going to extend the ideas to functions of 2 variables now. F at AB is a local maximum value of our function f, if and only if f at AB is always bigger than f at xy for all x and y close to AB. Same ideas as for mathematics 1, just increase the number of variables from 1 to 2. And of course, we can do the same thing for a local minimum. Almost exactly the same, but just change greater than or equal to less than or equal to. The first derivative test function f has a local extrema on an interior point AB of its domain. If that's true, if it has a local extrema at an interior point, then both of the partial derivatives, both of the first order partial derivatives of f at this point must be 0, as long as they both exist. Same ideas as for mathematics 1. If there's a local extrema, then the derivatives are 0. So for example, if we look at the top of this function, if we took the top of this hill, at this point, the x partial derivative and the y partial derivative are both equal to 0. An interior point of the domain of a function where one of these 3 things is true is called a critical point of f. Either both of the partial derivatives are 0, or fx does not exist, or fy does not exist. If one of these 3 facts are true, then it is called a critical point of f. So again, same ideas as for mathematics 1. Local maxima and local minima are not the only types of critical point. We might also have saddle points. Let's suppose our surface is shaped like a horse's saddle at one point, or if we prefer to think of it this way, let's imagine that part of our surface, part of our graph of a function, looks like a Pringles chip. Here is the graph of the function z is equal to y squared minus x squared. On this graph, the point 0, 0 is a critical point. The first order partial derivatives at 0, 0 are both equal to 0. But 0, 0 is not a local maximum, because if we let y change, the function goes up. And 0, 0 is not a local minimum, because the graph also goes the other way. It's not a maximum, it's not a minimum. This point is called a saddle point. Anytime we have this fact where if we look along one direction, the graph goes upwards, it opens upwards, but if we look in a different direction, the graph goes downwards, then it's called a saddle point. For example, find the local extrema of y squared minus 4y plus x squared plus 9. And I've put part of what we need here. We need to find the domain of this function, we need to find the partial derivatives, and we need to find where are the partial derivatives equal to 0. In other words, where are the critical points? And then we'll be able to answer the question. our function is just a polynomial. Power functions, y squared, x, etc., numbers, linear functions. So this is defined everywhere. This function has domain all of r squared. fx is 2x and fy is 2y minus 4. How do we get these equal to 0? We must have that x is 0 and y is equal to 2. So 0, 2 is going to be the only critical point of this function, as the only place where it's possible to have an extrema. So then we are asking, is 0, 2 a local maximum, a local minimum, or a saddle point? Now note that if we write our function as y minus 2 all squared plus x squared plus 5, if we complete the square, then we have something which is always greater than or equal to 5. It's always greater or equal to the value of f at the point 0, 2. So the point 0, 2 must be a local minimum. Let's do another one. This is almost the same, but look, now I've changed this plus to a minus. Find the local extrema of y squared minus 4y minus x squared plus 9. What is the domain? The domain is of r squared again. Calculate the partial derivatives, and again, we find that the only critical point is the point 0, 2. This is the only point where it's possible to have an extrema. Is it a local minimum? Is it a local maximum? The answer is no. First of all, what happens if we fix x equal to 0 and we let y change? Then we have y minus 2 all squared plus 5. And this function curves upwards like this. But if we fix y equal to 2 and then we have the function 5 minus x squared, we have a function which curves downwards. What do we have when we have a function which curves upwards in one direction, curves downwards in another direction? We have a saddle point. Now I'm going to show you the graphs of these two functions. On the left, we have the function that we looked at first. We've calculated that this must have a local minimum at the point 0, 2. Look at the picture, it does. And on the right, we have a function where we said it must have a saddle point at the point 0, 2. And now we can see from the graph that that's true. It does have a saddle point at 0, 2. The second derivative test. First of all, what do we need? Just to be careful, let's suppose that f, fx, fy, fxx, fyy, and fxy are all continuous on an open disk centered at AB. In other words, we'll just suppose we have a nice function. Nothing's complicated here. It's a nice continuous function. And I want to suppose that the point AB is a critical point. In other words, fx and fy are both equal to 0 at the point AB. Our theorem says if the second partial derivative fxx is negative at the point AB, and this number fx fyy minus fxy squared is positive, then we must have a local maximum at AB. If fxx is positive, and this number fxx, fyy minus fxy squared is also positive, then we have a local minimum at AB. If instead this number fxx, fyy minus fxy squared is negative, then we must have a saddle point at the point AB. And finally, if this number is 0, then we don't know. We would need to use a different test, a different type of mathematics to see what do we have at AB. Now, this number, this fxx, fyy minus fxy squared, has a name. And this is called the Hessian, or the discriminant of f. So if we were asked to find the local extrema of a point, or to find all of the critical points and classify them as local maxima, local minima, or saddle points, we want to calculate, first we're going to find all the critical points, and at each critical point we're going to calculate the Hessian. And if the Hessian is strictly positive, we go back, the Hessian is strictly positive, we're going to look at fxx, and that will tell us do we have a maximum or a minimum. If the Hessian is negative, then we will know that we have a saddle point. Let's do 3 examples from the book. Find the local extreme values of this function, xy minus x squared minus y squared minus 2x minus 2y plus 4. And I'm going to do this quickly. The function is defined and differentiable everywhere, so we're just looking for the points where the first order partial derivatives are equal to 0. So we're looking, where can we have fx equal to 0? Where can we have fy is equal to 0? And the answer is only when x and y are minus 2. So we're looking at the point minus 2, minus 2. We can calculate the second order partial derivatives, and then we can calculate the Hessian, or the discriminant of f at minus 2, minus 2, and we get 3. What do we know if the Hessian is a positive number? We know that we must have a local maximum or a local minimum. So then we look at fxx. Is this positive or is this negative? This is negative. If the Hessian is positive but fxx is negative, then we must have a local maximum. Next example. Different function, 3y squared minus 2y cubed minus 3x squared plus 6xy. Again, this function is defined everywhere, it's differentiable everywhere. So we're just looking for the points where the first order partial derivatives are, are equal to 0. And I'm going to skip the details. You can check this. The critical points are 0, 0, and 2, 2. But are these critical points local maxima, local minima, or saddle points? We calculate the second order partial derivatives, and we calculate the Hessian, or the discriminant. And then we ask, what happens at the point 0, 0? What happens at the point 2, 2? At the point 0, 0, the discriminant, or the Hessian, is minus 72. What do we know from that? We know that we must have a saddle point. Let's move on to looking at the point 2, 2. Now the discriminant has a positive value, 72. If the Hessian or the discriminant is a positive number, we have either a local maximum or a local minimum. But which is it? We look at fxx, and that's a negative number. Positive Hessian, negative fxx, we must have a local maximum. You can find a graph of this function in your textbook. One more example. Find the critical points of 10xy e to the power minus, open bracket, x squared plus y squared, close bracket, and use the second derivative test to classify each point as either a saddle point, a local minimum, or a local maximum. The first thing to do is to find all of the critical points. So first, we're looking where fx is equal to 0, and where can we have fy equal to 0. And we need both of these to be true at a point. It's not just good enough to have one of the partial derivatives equal to 0 and not the other one. We need to have both of these equal to 0. And I'm going to leave it for you to check the details here. You can check that there's actually 5 critical points of this function. The next step is to calculate all of the second order partial derivatives. Again, I'm going to be quick. You can come back here, you can read your textbook and check the details. And then then the book is calculating the values of these second partial derivatives and the discriminant or the Hessian at each of these points. First, at the point 0, 0, the Hessian or the discriminant is a negative number, so saddle. Let's see if I can write on here. Okay. Let's look at the second one. Now the discriminant is a positive number. In fact, for all of the other ones, the discriminant is a positive number. These are all local maxima or local minima. So we look at fxx. Are these numbers positive numbers or negative numbers? If it's a negative number, we have a maximum. If it's a positive number, we have a minimum. The fourth one, positive number, minimum. And the last one, fxx is a negative number, so we must have a maximum. Let's move on to a different type of question. Find the absolute maximum and absolute minimum values of this function on the triangular region drawn here. It's the triangle which is bounded by x is 0, y is 0, and y is equal to 9 minus x. Or to say it another way, it's the triangles with corners at the origin, at 9, 0, and at 0, 9. How are we going to answer this? We're going to look at the interior of the region. We've been looking at interior points before. We'll use the second derivative test on the interior. We're going to look at the corners, O, A, and B. And we're going to look at the three sides, the line from O to A, the line from O to B, and the line from A to B. And we're going to be looking at these 5 things separately. First, let's look at the interior of the region. I misspoke. I said second derivative test, I meant first derivative test. We look for the critical points. Where do we have fx equal to 0 and fy equal to 0? Only at the point 1, 2. And then we calculate the value of f12, and that's equal to 7. We will need that later. So I'm going to put that in the blue box. The blue box is going to be everything that we need later. Step 2, we should look at the corners of this region. You can calculate the value of f at the corners. F at 0, 0 is 2, f at 9, 0 is minus 61, and f at 0, 9 is minus 43. We will need these numbers later, so let's put them in the blue box. Step 3. Let's think about the line from O to A. If we're on this line, then we always have that y is equal to 0. So on this line, we're looking at f at x 0, where x is some number between 0 and 9. So in other words, we're looking at 2 plus 2x minus x squared. What are the critical points of this function? Only x equal to 1. So we want to calculate f at the point 1, 0, and we find that that is equal to 3. And let's put this number in the blue box. Step 4, let's look at the line from O to B. If we're on the line from O to B, then we must have the x is 0. So now we're looking at f at 0y for any number y between 0 and 9. What are the critical points of 2 plus 4y minus y squared? Only y equal to 2. So we want the value of f at the point 0, 2, and that's 6. Again, let's put that in the blue box. One more thing we need to look at. We need to look at the line from A to B. On this line, we have that y is equal to 9 minus x. So on this line, we have f at x, comma 9 minus x. And that is actually, and you can check this, minus 43 plus 16x minus 2x squared. What are the critical points of that function? The only critical point is when x is equal to 4. So we want the value of f when x is 4, and if x is 4, y must be 5, because x plus y is 9. F at 4, 5 is minus 11. Again, let's put this in the blue box. So to recap, first we looked at the interior, and we found there's only one critical point in the interior. We looked at the corners. We might need the corners, so we'll do those. We looked at each of the 3 sides, and on each of the 3 sides, again, we found just one critical point. If you look at this picture, we've been calculating the value of f at each one of these 7 red dots. The local maximum must be at one of these 7 red dots, and the local minimum must be at one of these 7 red dots. But which is it? we've found 7 values of f. We found the numbers 7, 2, minus 61, minus 43, 3, 6, and minus 11. Which of these numbers is the biggest number? 7. Which of these numbers is the smallest or the least? Minus 61. And that's how we answer this question. The absolute maximum of f on this region must be 7. The absolute minimum value of f on this region must be minus 61. That's the method if we're given a question like this. Look at the interior, calculate the f at all the critical points, calculate the value of f on all of the corners, and then look at each edge separately, find the critical points on the edge, now that you only have a function of one variable, and calculate the value of f at every one of these critical points. Make your list of numbers and find the biggest number and the smallest number. And then you have your answer. There's another example in the textbook. It just does almost exactly the same as what we've just done. So I'm going to leave that for you to read. Please read example 7 in section 13.7. It's the same type of question that we've just done. The final topic for today is Lagrange multipliers. That's the final topic which might or might not appear on your midterm exam. So listen carefully for this, for one more section. I want to answer questions like this. Find the point P on the plane 2x plus y minus z minus 5 is equal to 0 that is closest to the origin. Now we want to find the minimum of a function. In this case, we want to find the minimum of the distance. So we want to find the minimum of the square root of x squared plus y squared plus z squared. But the extra complication is it's not the minimum across the whole of R3, it's the minimum subject to an extra constraint. And in this case, it's the subject to the constraint that 2x plus y minus z minus 5 is equal to 0. And that's the idea in this section. We're going to be finding the minimum or the maximum of a function subject to some constraint, subject to some condition. Now, this time we have a square root, and square roots can maybe be a little bit complicated. We don't need that. Instead, let's look at the function f is equal to x squared plus y squared plus z squared. Instead of looking at the distance between O and P, we're going to look at the function of f. We're going to find the minimum of f subject to the constraint that 2x plus y minus z minus 5 is equal to 0. And we're going to see where does that happen? Where is this minimum? In the constraint, we had x, y, and z. 2 of these we're going to let be independent variables, and then the other one is going to be defined by the equation. So we could write z is equal to 2x plus y minus 5. I could put that into f. So instead of looking at f, y, z, I'm looking at f, x, y, 2x plus y minus 5. And I'm going to call that h. We can use the first derivative test to find the critical points of h. So differentiate h with respect to x, differentiate x with respect to y. You can check these. We end up with two equations. 10x plus 4y is 20. 4x plus 4y is 10. Solve these equations. We need to have x is 503 and y is 506. And after we know x and y, we can find z. So the answer to this question is that the point on the plane which is closest to the origin is 503, 506 minus 506. And that is a correct answer, but that's not the easiest way to solve this question. It's easier to solve a question like this if we use the method of Lagrange multipliers. In general, let's suppose we want to find the maximum or the minimum of some function f, subject to the constraint that g is equal to 0. The method of Lagrange multipliers says we only need to find x, y, z and another number lambda which satisfy nabla f is equal to lambda nabla g and g is equal to 0. And in practice, that's going to be easier for us to do. Now, this is the rule if we have three variables, x, y, and z, but that's not always going to be true. Sometimes we'll only have two variables. Just cross z out on the slide and it's still true. If we want to find the maximum minimum of f of x and y, subject to the constraint g of x and y is equal to 0, then we only need to find x, y, and lambda, which satisfy nabla f is equal to lambda nabla g, and g of x and y is equal to 0. In other words, if you don't have a z, just ignore it, just forget it. Let's do the previous example again. Find the point P on the plane 2x plus y minus z minus 5 equal to 0, which is closest to the origin. We've just done this, we know the answer. But now I'm going to show you how it's easier if we use the method of Lagrange multipliers. I've put the two equations that we need at the top. We need nabla f is equal to lambda nabla g, and we need g of x, y, z is equal to 0. One of our functions here, our function f is x squared plus y squared plus z squared. This is the function that we're trying to find the minimum of. And our constraint is that g is equal to 0. I'm going to start with the first equation. I want to start with nabla f is equal to lambda nabla g. What is nabla f? Nabla f is 2xi plus 2yj plus 2zk. What is nabla g multiplied by this extra constant lambda? 2 lambda I plus lambda j minus lambda k. Right, differentiate g with respect to x, we get 2. Differentiate g with respect to y, we get 1. Differentiate g with respect to z, we get minus 1. And then multiply everything by lambda. Okay, so 2xi plus 2yj plus 2zk must be the same as 2 lambda I plus lambda j minus lambda k. So x must be the same as lambda, y must be the same as lambda over 2, and z must be the same as minus lambda over 2. What we're going to do is we're going to take these and we're going to substitute them into the second equation, into g equal to 0. 0 is equal to 2x plus y minus z minus 5. Instead of x, I'm going to write lambda. Instead of y, I'm going to write lambda over 2. And instead of z, I'm going to write minus lambda over 2. There it is. And that simplifies to 3 lambda minus 5. What we have is 3 lambda minus 5 is equal to 0. So lambda must be 5 over 3. But then look what we have. Now we know lambda. If we know lambda, then we know x, y, and z. So the point that we want must be the point 5 over 3, 5 over 6 minus 5 over 6. And look how much easier that was. Last time I solved this example, I needed more than one slide. I needed 2 slides full of maths, but this time I've solved the same problem, but only using 1 slide. Let's look at some more examples. This time, let's look at examples from the textbook. Find the greatest and smallest values of the function xy, so the maximum value and the minimum value, subject to the constraint that x squared over 8 plus y squared over 2 is equal to 1. We have our first function f. We need our second function g, and then we want to set g equal to 0. So g would need to be x squared over 8 plus y squared over 2 y squared over 2, and then minus 1. The constraint is then just g equal to 0. So here we are. We have our f, we have our g. To use the method of Lagrange multipliers, we need to find x, y, and lambda such that nabla f minus lambda nabla g and g is equal to 0. Start with the first equation. Nabla f is just yi plus xj. Nabla g is a quarter xi plus yj. So y must be the same as lambda over 4x, and x must be the same as lambda y. From this, we find there's 2 possibilities. Either y is equal to 0, or lambda is plus 2, or lambda is minus 2. We're going to do these 2 cases separately. First, what do we have if we have y equal to 0? But then we would have x equal to y equal to 0, but 0, 0 is not on the ellipse. So this can't be true. Forget about this one. Next, let's look at case 2. If y is not 0, then lambda is either plus 2 or lambda is minus 2. But then x must be plus 2y or minus 2y. Now that we know this, we can move on to the second equation. Now we pick up our second equation. Now we take g is equal to 0, and we put this information in. And I leave it for you to check, but after we've simplified this, we find that y must be plus 1 or y is equal to minus 1. So our function f must take its extreme values when y is plus 1 or y is minus 1. you think of our ellipse, it looks like this. That gives 4 points. +1, -1, +1, -1. We're either 2, 1, or 2, -1, or -2, 1, or -2, -1. And at these points, x, y is either equal to 2 or is equal to -2. So these must be the extreme values. Let's do another example. Find the maximum and minimum values of the function 3x plus 4y on the circle x squared plus y squared is equal to 1. What do we need first? First, we need our two functions, f and g. So we write those down. And then we're going to be looking for the values of x, y, and lambda, which satisfy the equations nabla f is equal to lambda nabla g, and g is equal to 0. From the first one, from nabla f is lambda nabla g, we find that x is 3 over 2 lambda and y is equal to 2 over lambda. Check that. And then we can put that into the second equation. We take these and we're going to put these into g equal to 0. And I'm skipping the details. Once we've done that, we can find that lambda is plus 5 over 2 or minus 5 over 2. As soon as we know lambda, we know x and y, and then we're almost finished. A little bit of calculation and we can finish this question. But that's enough from me this week. Next time, after your exam, we will start talking about integration again. Double integrals and integrated integrals over rectangles or over general regions, area by double integration, and then to get ready for the following lesson, I'm going to introduce polar coordinates. Are there any questions?